Hello everyone, I am Dr. Ritish Kumar, Assistant Professor in Department of Electronics and Communication Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. So in this lecture we will discuss the topic of radar, that is in the subject of microwave and radar engineering. So what is the radar? Radar is nothing but radio detection and ranging. Radio detection and ranging, as name suggests, it is a system to detect a target or something else with the help of uh, radio waves. That's why we called the name of radio detection and ranging, and we are also able to know the range of the target from the radar or from the antenna as well. So this is the basic knowledge we need to know what is the radar. So let's begin with the lecture. First, before starting the topic of radar, we need to understand the different bands that lie in the microwave region, such as L, sorry, such as L, S, C, X, Ku, K and K. These are the important band that we need to know for the microwave subjects. So it starts from 1 up to 40 gigahertz, and different frequency range has different name. For the L band, it has the value of 1 to 2 gigahertz. For S band, it has the value of 2 to 4 gigahertz. Similarly, for C band, 4 to 8 gigahertz. X band. So in the laboratory, in our laboratory, we mostly we have done mostly the experiment within this range, that is 8 to 12 gigahertz, and that band is known as X band here. Now the Ku band, K and K band. So Ku band 12 to 18 gigahertz is mostly used for the satellite communication point of view. That's why we have mentioned the application of here, the satellite communication and microwave experiment. Now the beyond the 40 gigahertz, the band name is known as millimeter wave band. Now corresponding to this frequency range, we have mentioned the wavelength, that is in the third column. So you can observe here the wavelength is coming in the unit of millimeter. So wavelength is in the range of millimeter. That's why we call this band is known as millimeter wave band. But here you can clearly observe here, in the case of microwave bands, we have the wavelength in terms of centimeter, right? So microwave band also known as centimeter wavelength. Why? Because if we calculate the radiating energy with the help of the formula of E is equal to hc/by lambda, where h is equal to Planck constant and c is equal to speed of light, and lambda is the wavelength of the signal. If we calculate the if we put the value of wavelength in terms of centimeter, then after putting all the values of Planck constant, speed of light and the wavelength, we will have the value of energy in terms of 10 to the power minus 6 in multiples of 10 to the power minus 6, that is the micro. So from the centimeter wavelength gives the radiating energy in the microwave in the unit of micro electron volt. That's why we call this band is a microwave band. This is the basic knowledge that we we need to know. Now these three band, high frequency band, very high frequency band, and ultra high frequency band. Frequency comes into the megahertz range, and the corresponding applications are mentioned in the third column, that is televisions, FM broadcasting, and telephone is the main application of this of these three bands. So mainly these are the microwave bands that we need to know. And here we have mentioned for the radar experiment, mostly the band that that are being used is the millimeter wave band. So this is about the frequency bands in the microwave subjects that is very important. And this kind of question may be asked in the examination as well. What is the electromagnetic spectrum, and mention the different kind of bands in the electromagnetic spectrum for the microwave frequency range. In that case, you need to give the answer with the help of this table. This is very simple one, so you can by looking this table you can able to give the answer. Next one, radar block diagram. As name suggests, what is the full form of radar? Radio detection and ranging, right? So as name suggests, as I discussed previously, you are able to detect something, that is the target here, with the help of radio waves. And you are also able to know the range of the target. That target could be anything, right? Here I have taken the target as an aeroplane. Now I have mentioned the basic block diagram of the radar here. Now you can see transmitter is here, duplexer switch is here, antenna is here, receiver is here, signal processor is here, data processor is here, unit display, and the target, right? So everyone knows what is a transmitter. Transmitter is used to transmit something. It generates a signal that is a kind of, here we are using the high frequency signal in the form of pulse form. So mostly in the radar, time domain pulses are used to transmit the data, to transmit the pulse, and with the help of these pulse we can able to detect the target. Here mostly we used the signal in the pulses form, right? Here you can see the duplexer switch. So duplexer is nothing but a TR switch. TR switch means transmitter and receiver switch. So at a time this switch is linked over the transmitter whenever the transmitter whenever this system is in the transmitter mode. Whenever the system is in the receiver mode, this duplexer switch is shifted towards the receiver side, so it can switch from transmitter to receiver transmitter and to receiver in the system. That's why we call this one is a TR switch as well as the duplexer, because it has two functions. Now transmitter generates a high impulse uh, uh, very thin pulse, means very thin impulses signals, and that pulses signals is transmitted through this antenna convert this signal into the electromagnetic waves, and this electromagnetic signal is is direct towards the target. And if whenever the targets comes into the picture, this signals there is a kind of mismatch is happening between the free space and the target. So it could possible to have some reflection, could not could it always be in that case we have a reflection from the target. So the reflection signal is known as echo here, right? This reflected signal is known as echo. This echo signal is received by the same antenna which has been used for the transmitted signal. So I will discuss why we use the same antenna as a transmitter and receiver here. First I will cover this block diagram here. So after receiving this echo signal from the antenna, then this duplexer switch is shifted from transmitter to receiver side, and this signal is received by this receiver, and receiver has its own functioning. So in the communication system, as we read as we already read that at the receiver point a super heterodyne receiver is there. In the super heterodyne system, the first section is a LN amplifier. So LN is a low noise amplifier, that is nothing but it amplify the signal by reducing the noise. So here you can use the low noise amplifier here, but that low noise amplifier designed according to the microwave frequency here. So receiver passes the signal to the signal processor. So you can modify the signal according to your desiredness, whatever kind of signal you want to look at the display unit. So according to yourself, you can decide what kind of signal representation you can look over the display unit, and whatever the signal processing you will do over the received signal, and that data you can collect in the data processor, and that data processor and whatever the data you will collect by using the signal processing you can display by using the display unit. And by using the display unit you can able to you can decide the range and the location of the target, location of the target, that is the range of the target, and how it can possible to find the range of the target. As you for the suppose for the stable target, you know the separation from this antenna to target, and by using the simple time and you know the received time, you know the difference between the transmitted signal and the received signal, you know, right? You know the time traveled by the transmitted and received signal, and with the help of these two data you can able to find the range of the target. Now the thing is I will explain how can we able to find the range of the target here. Now the thing is the same antenna, how can a antenna be possible to act as a transmitter and receiver at a time, because this concept arises from the reciprocity theorem in the antenna or in the circuit theory as well. So, by replacing the source from one branch to another branch, and you can calculate the current from replaced branch to another branch, and if you take the ratio of these two, voltage and current, you are that is known as the reciprocity theorem at a time. Now here the same concept is here, from the reciprocity theorem, write down the reciprocity theorem. So from the reciprocity theorem, this antenna can act as a transmitter and receiver simultaneously. This is the basic knowledge you should know as well. Now the next slide I will discuss the thing radar range equation. As I told you, with the help of the radar you can decide the range of the target, and for this a derivation for it, how can we able to decide the range of the target as well. So you can see here, if the transmitter delivers the power PT watt here into the isotropic, and here we are using the isotropic antenna here. So power density at a distance of r, that is equal to PT upon 4 pi r square. PT, the unit of it is watt per meter square. So obviously this is a power density here, and r is the distance between the radar and the target. So 4 pi r square represent the surface area of sphere at a distance r. So actually here we are transmitting the signal with the help of the antenna, and antenna has its own directivity and own gain. So for this, if the power density PT upon 4 pi r square, and we have a antenna gain is G, or then the power density we can have by using the antenna gain. So we need to multiply this power density with the antenna gain, that is PTGT, or we can say PTG upon 4 pi r square. This one is only for the directional antenna. The first one is used for the isotropic antenna as well. So the thing is, the incident power is intercepted by the target, and a portion of signal is redirected to the radar based on radar cross section area. So radar cross section area is represented by sigma, right? Every target has its own area, that area is known as radar cross section area. So because so power density of echo signal, echo means the reflected signal that is reflected from the target, and that density we can get from this equation. Sigma, we need to multiply by sigma upon 4 pi r square. So we need to take the relative area of radar cross section system here. So now the power delivered to the receiver is given by equation this one, where AE is the, what is the AE? AE is the effective aperture area of the antenna. Effective aperture area. Why? Because whenever the signal is received by the antenna, so some part of the antenna is in the working mode, and I mean to say the full area cannot be considered in that case. Only the some part of the antenna is affected by the echo signal. So that's why we need to take the effective area of the antenna here. And the next one, the the relation between effective area and the gain of the antenna is represented by G is equal to 4 pi upon lambda square into A, where G is the gain of the antenna. So by putting these value in the previous equation, so we have a R maximum here. So R maximum is the maximum distance which is detected by the radar. In other words, we can say this is the distance, this is the maximum distance, that is this is the distance where the minimum power can be detected. So the minimum power minimum power is directly related to the maximum distance here. So this is the another form of the maximum range of the radar that can be calculated by the radar system. Now if the radars is transmit and receive, these are another other two forms we can see. So if you put this gain value in this equation, suppose A is here, you can take the value of A from this equation and put A value in this equation, then you will get the R maximum in this form, right? If you put the value of gain in this equation, then you will have the R maximum in this form, right? So these are the another form of maximum radar range, right? I think this is clear to all of you. Next, what is the Doppler radar? So as we know, the radar radiates electromagnetic waves towards the target for detection and also to obtain details of the target. What kind of details? The range, and either the target can be in the condition of movable or stationary, that also we can get to know with the help of radar. When the target is stationary, as I have mentioned here, what will happen? The frequency target is stationary, the frequency of the received echoes is constant, right? Because the distance is same between the distance, suppose this is an antenna, if the distance between the target always, right, then the frequency of echo signal is always be constant. Suppose if the target is moved towards the radar and target is moved away from the radar, then what will happen? If the target is moving towards the radar, then then this target comes closer to the radar, and in that case the received echo signal frequency will increase, while in the case of when the target is moving away from the radar, in that case the signal strength is also weaken, the signal strength of the echo signal is also weaken, and the frequency of the signal will decrease in that case. So this is how we can understand either the target moving towards the radar or away from the radar. This is the method. Now the presence of the obviously if this target is moving from its reference point, then the frequency is shifted toward the lower or higher side, and that shifting of the frequency is known as Doppler effect, or in terms of frequency we can say this is a Doppler frequency shift, right? I think this frequency shifting concept by using a stationary object, a stationary target, or by using moving object or moving target, right? How the frequency shifted in that Doppler radar, right? In the next what is the Doppler frequency? So for this we need to derive the equation for the Doppler frequency. What is the Doppler frequency, as I discussed? So omega d is the Doppler frequency in radian form. if I say this is 2 pi fd, omega is equal to 2 pi f, if the omega is equal to d phi by dt, and we know this is a phase difference, and we know that phi is equal to 2 pi by lambda, right? And we know from the antenna, if the target has a distance of r, so total distance traveled by the signal is 2r, then we need to take 2r, so path difference, then we have total path traveled by the electromagnetic event, then phi is equal to, we have 4 pi upon lambda. That's why phi is equal to 4 pi r upon lambda, right? So here this is a constant term, and dr by dt, and dr by dt is also known as velocity of the relative velocity of the target. So this is 4 pi vr upon lambda. Now this is equal to 2 pi fd. 2 pi to 2 pi cancel out 2 times. Finally we have fd is equal to twice vr upon lambda, where fd is the Doppler frequency shift in hertz, vr is the relative velocity with respect to the radar, or with respect to the this is the velocity of target, lambda is the wavelength in meter. So the relative velocity is also written in the form of vr is equal to v cos theta. Why? Because it makes some angle, this is target and this is the angle of theta, and this is the velocity of b, so the relative velocity is v cos theta. That's why v cos vr is equal to v cos theta. Here we can take it here. Now in the next, as we know, Doppler frequency is twice vr by lambda, and vr is equal to twice v cos theta, as we discussed in the last one. So fd is equal to twice v cos theta by lambda. So from this equation we can conclude one, if theta is equal to 0 degree, then what will happen? If theta is equal to 0 degree, that means in that case we have a maximum value of Doppler frequency shifting, right? And that's why we have written over here, if theta is equal to 0, Doppler frequency is maximum, mean the target is just in front of the radar. If the target is just above the radar, that is, if it is make the 90 degree, the Doppler frequency is 0 in that case. Means the Doppler frequency is 0 when the trajectory is perpendicular to the radar line of sight, that is 90 degree. These two points are most important to understand the frequency, Doppler shift frequency. So this is about the Doppler radar. I think in this lecture we have covered the topic of frequency bands and the basic block diagram of radar and radar range equations, and the most important things were the shifting in the frequency, that is known as a Doppler frequency shift. That is the basic concept that you need to understand in the radar topic. I think these all are clear to all of you. Thank you everyone.